Hi everyone, this is Dr. Bay and here's Bugsy, and today we're going to go over aromaticity, so stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Many derivatives of benzene were originally isolated from fragrant balsams or sweet-smelling resins and oils obtained from trees and plants. These compounds were described as aromatic in reference to their pleasant odors and were often used in perfumes and even medicines. Even though chemists later discovered that many derivatives of benzene were actually odorless, the term aromatic was still used to describe these compounds. Aromatic rings, such as benzene rings, are a particularly common structural feature in a lot of drug molecules like Zyrtec, shown on the left, morphine in the middle, and Allegra, shown on the right. So what makes a structure aromatic? All of the following criteria have to be met in order for a compound to be considered aromatic. First, the molecule must be cyclic or ring-shaped. If the molecule is linear, then rule number 1 has already been broken. Second, the molecule must be planar or flat, which means that all atoms in the ring should be sp2 hybridized. Third, the molecule must be conjugated all around the ring. This means that there should be adjacent, parallel, overlapping p orbitals as shown in the benzene ring above. This allows for the pi electrons within the p orbitals to freely flow through the ring. And fourth, it should follow Huckel's rule, where 4n plus 2 equals the number of pi electrons, where n is equal to an integer or whole number. In the example on the right, benzene contains 6 pi electrons, so we'll set the equation 4n plus 2 equal to 6. Now if we solve for n, we find that n equals 1, which is an integer, meaning that benzene is indeed aromatic. Now if rules 1, 2, and or 3 are violated, then the molecule is not aromatic. But if rules 1 through 3 are still met, but n does not equal an integer, then the molecule is anti-aromatic. In the next example, cyclobutadien contains 4 pi electrons, so we'll set the equation of 4n plus 2 equal to 4. When solving for n, we find that n equals 0.5, which is not an integer. This means that this molecule is anti-aromatic, even though it still fulfills rules 1 through 3. So benzene is not the only compound that exhibits aromatic stabilization. As long as the molecule satisfies the 4 rules we just discussed, then the molecule is aromatic. Here are some examples of aromatic molecules: naphthalene, pyridine, furan, and cyclopentadienyl ion. Now, one thing that is important is how to figure out when lone pair of electrons are considered pi electrons, especially when there are lone pairs on more electronegative atoms like nitrogen, oxygen, or even sulfur, for instance. Remember that every atom in the ring should be sp2 hybridized, which means that the atom should have a total of 3 steric groups connected to it. Recall that double bonds count as one steric group, and each lone pair of electrons also counts as one steric group. Every carbon atom in benzene is sp2 hybridized because each carbon is connected to one hydrogen atom, one carbon single bond, and one carbon double bond, totaling to 3 steric groups. If a lone pair is part of sp2 hybridization and resides in an sp2 orbital, then it is not counted towards pi electron count. In the example on the right, let's first determine the hybridization of the nitrogen atom to determine if the lone pair on N should or should not be counted as pi electrons. The nitrogen atom in pyridine is sp2 hybridized because nitrogen is connected to one lone pair of electrons, one carbon double bond, and one carbon single bond, totaling to 3 steric groups. This means that the lone pair on nitrogen will not count towards the pi electron count. Now, if we look at the structure of pyridine, since it contains 3 alkenes, that means that pyridine has a total of 6 pi electrons. So we will set the equation of 4n plus 2 equal to 6. Now, after solving for n, we find that n is an integer of 1, which means that pyridine is indeed aromatic. On the other hand, if a lone pair resides in a p orbital, then it is included in the pi electron count. In the example of furan on the right, let's first determine the hybridization of the oxygen atom to determine where each lone pair of electrons reside in. Remember that in order for a molecule to be aromatic, all atoms in the ring must be sp2 hybridized. For the oxygen atom to be sp2 hybridized, its 3 steric groups are a carbon single bond to the left of O, another carbon single bond to the right of O, as well as 1 lone pair of electrons. This means that the second lone pair of oxygen resides in a p orbital, which means that it does count towards the pi electron count. Now if we look at the structure of furan, 4 of the pi electrons come from the 2 alkenes, and then 2 more pi electrons come from the second lone pair on oxygen. This means that furan has a total of 6 pi electrons, so we can set the equation of 4n plus 2 equal to 6. And since n is an integer of 1, this means that furan is aromatic. Now let's determine if the following molecules are aromatic, anti-aromatic, or not aromatic. For your convenience, I listed the aromaticity criteria again on the left-hand side. In example A, the molecule is cyclic, however, it is not planar. The carbon atom at the bottom is sp3 hybridized because it is connected to 2 hydrogen atoms. Recall that sp3 hybridized atoms have a tetrahedral geometry which is not planar. So this molecule breaks rule number 2. Also, this molecule is not fully conjugated. Remember that a conjugated molecule has to have at least 3 consecutive p orbitals in a row, which for most part means an alternation between single bonds and double bonds all around the ring. Since there's a break in conjugation due to one sp3 hybridized carbon atom, rule number 3 has also been broken. As soon as you see any of rules 1 through 3 broken, that means the molecule is not aromatic. Now let's take a look at example B. The molecule is cyclic and planar because all atoms in the ring are sp2 hybridized. The carbon atom with a positive charge, also called a carbocation, is sp2 hybridized since it is connected to 2 carbon single bonds and a hydrogen atom, which means that it has a total of 3 steric groups. The positive charge means that it contains an empty p orbital that pi electrons can flow into, which takes us to the third rule. The molecule is fully conjugated because of that empty p orbital. Now let's look at Huckel's rule. This molecule has 3 alkenes, which means it has a total of 6 pi electrons. So if we set 4n plus 2 equal to 6, this tells us that n equals to 1, which is an integer, so this molecule is aromatic. In example C, the molecule is cyclic, planar, and fully conjugated. Remember that this molecule is drawn as bond line structure, so the carbon with the lone pair, also called a carbanion, has 1 hydrogen atom connected to it in order for that carbon atom to have a -1 formal charge. Since the carbon atom is sp2 hybridized due to it being connected to 2 carbon single bonds as well as a hydrogen atom, that means that the lone pair resides in a p orbital, so we will consider it in our pi electron count. That means that this molecule has a total of 6 pi electrons where n equals 1, so the molecule is aromatic. And lastly, in example D, the molecule is cyclic, planar, and fully conjugated. But since it has 4 alkenes, that means this molecule contains a total of 8 pi electrons. If you set 4n plus 2 equal to 8, you get n equal to 1.5, which is not an integer because it's a decimal. Because of this, the molecule is anti-aromatic. In summary, we learned that aromaticity is a property of cyclic planar structures with pi bonds in resonance that gives increased stability in comparison to other structural connectivity arrangements with the same set of atoms. Anti-aromatic compounds also contain a planar closed loop of p orbitals, but with 4n pi electrons, and these types of compounds are less stable than aromatic compounds.
Organic.